Let us talk about this problem. We are given a sorted array and a number x. Our target is to find index of first occurrence of this number x in the sorted array. So our sorted array might contain duplicates and we need to find index of first occurrence of the given element, and if the given element is not present, we need to return -1. Let's understand the problem with these examples. So we have a sorted array and a number x20. Where does 20 occur first time? 0, 1, 2, 3, 4 at index 4. So our output is 4. X is 15. 15 is not present in this array, so our output is -1. X is 15 and 15 is present at 0 index itself, so our output is 0. Now please pause this video and try to write down a function that takes an array as an argument and returns index of first occurrence of a given element in the array. Let us first talk about a naive solution to solve the problem. The naive solution is traverse through the array. As soon as you find the given element, you return that index. And if you traverse through the whole array and you don't find the element, you return -1. So we run a loop from 0 to n-1. We compare every element with the given element that we are searching, whose first index we are searching. If we find it, we return I. Since we are traversing from left to right, we will return as soon as we find the index. So in this example, we'll run a loop for 0, 1, 2, 3. So when we come to 3, we return 3, right? This line will execute and we'll get 3, right? And when we come out of the loop and we don't find, suppose I'm searching for something like 25, right? So I'll traverse through till end and I won't find 25, so I'll return -1 after coming out of the loop. So time complexity of the solution is big O of n, and this solution requires big O of 1 auxiliary space. This is big O of n time and big O of 1 auxiliary space. Now please pause this video and try to write down a solution that works in big O of log n time. Let us now talk about a log n solution. In this implementation, we are going to use binary search, and first we are going to write code using recursive binary search. Then we will talk about iterative binary search code. Please remember, iterative would be better because recursive code will take log n extra space, big O of log n extra space, and it will also cause unnecessary function call overheads. Let's first do a recursive code first because it's easier to relate the recursive code with the approach. So the idea of recursive code here is, it's like binary search. Suppose this is the example and we are searching 20. We go to the middle index, right? We write a recursive code that takes a start index, end index, low and high, and it also takes the element being searched, right? It finds the middle element, goes to the middle element, right? And if the element to be searched is greater than the middle element, like in this case, we are searching for 20 and it's greater than 15. So what we do, like binary search, we go to the right half. And if the element to be searched is smaller than 15, say the searched element was 2 instead of 20, then we would have gone to the left half, like we do in binary search. The only difference here is when the element is same. What do we do in that case? If the element is same, then it might or might not be the first occurrence of that element. Let's see what happens in this example. So we see that 20 is greater than 15. So we go to the right half, we go to this half. Now we go to the mid and we see that 20 is same as 20. So what should we do now? We check whether it is first occurrence or not. And how do we check? We compare it with the previous element. It's just a constant amount of work, right? If it is same as previous element, then it is not first occurrence. So in that case, we recursively call for left half of this subarray. And if it is first occurrence, then we return it first occurrence. That's the idea. Now please pause this video and complete this recursive code yourself. You can definitely do it with these ideas. Please make sure that you handle the corner cases really well. For example, if your array is something like 5, 5, 5 and you're searching for 5, then you will reach 0 here, right? And if you go back and look for the previous element, there's no previous element, right? So make sure that you write nice code to handle this case as well. Let us now see recursive implementation of the approach. So in the recursive implementation, we have basic logic same as normal binary search. We check whether low is greater than high. If low is greater than high, then we have reached a corner case because they crossed each other. In those cases, we return -1, right? Like we do in the normal binary search. Then we compute the midpoint. low plus high by 2, right? After computing the midpoint, if x that we're searching is greater than mid, then we go to the right half, right? We go from mid plus 1 to high. And if x is smaller than mid, then we go to the left half, right? Low to mid minus 1. Now, if x is equal to mid, what do we do in this cases? So this case has two sub-cases now. If mid is 0, then it's a first occurrence, or array mid minus 1 is not equal to array mid, then also it's a first occurrence. So in those cases, we return mid because mid is our first occurrence. Otherwise, where do we go? We go to the left half because this is somewhere middle occurrence and we are looking for first occurrence, so we need to go to the left half. So this is the binary search based recursive code. If you take a look at this, its time complexity is also upper bounded by log n because in every recursive call you are either returning or you are dividing your input range into half. So the recurrence formula for time complexity becomes Tn equal to Tn by 2 plus you are doing some constant work, this condition check, this mid computation. So all that is constant work. Tn equal to Tn by 2 plus some constant whose solution is big O of log n. Now please pause this video and try to write down an iterative solution because this recursive solution involves function call overhead and extra space for recursive calls, extra log n space. Let us now see iterative implementation. In this implementation, we take log n time and big O of 1 extra space. So if you take a look at this code, this implements the same idea as we did in recursive solution. Like normal iterative binary search, we initialize low as 0 and high as minus 1. We run a loop. We have mid equal to low plus high by 2 and we check if array mid is greater than x, then we need to go to the left half because mid is greater, so you need to go to the left half. So to go to the left half, you do high equal to mid minus 1. If array mid is smaller than x, then you need to go to the right half. So this is normal binary search logic. And we come to this part when array mid is equal to x. So in this case, we check whether it is first occurrence or not. And how do we decide that this is first occurrence or not? If mid is 0 or mid minus 1, array mid minus 1 is not same as array mid. If any of these two cases are true, then it's a first occurrence. So we return mid. And if it's not first occurrence, then we go to the left half. To go to the left half, we change high equal to mid minus 1. Let's now see the working of this function for this example. Say we have this array and we are searching for x equal to 10. So what we do? We compute the mid is 0 plus 4 by 2, 2, right? So we come here and this is same as x, right? So if it is same, then we check if the previous element is same or not. So previous element is same and it's not 0. So we come to the else part. So we go to the left half. So to go to the left half, our high changes to 1, right? So we change high to 1. Now the second iteration of the loop begins. In the second iteration, we again compute low plus high by 2. So low was 0 and high is now 1. So 0 plus 1 by 2 is 0. So we get the mid as 0. Now we again check which case we are in. So we compare array mid with x and x is greater than array mid. So we go to the right half. When you go to the right half, you change low to mid plus 1. So your low becomes 1. Now you begin the next iteration. And in the next iteration, your high is 1 and low is 1. So you compute the mid as 1. When you compute the mid as 1, you notice that you are at this index and this is same as x. When this is same as x, you check whether mid is 0, no. In array mid minus 1 not equal to array mid, yes. So you fall into this condition, this is our logical OR, you return mid. So you return 1 as an index of this 10. So this is iterative solution, the best solution among all the solutions that we have discussed so far.